Hello everyone, welcome back to ptet.chemistry channel. So in this restructured format tutorial, I'll go through this 9701. This is a fairly recent paper. This is for the June 2021. This is paper 1-1, so it's an A-level chemistry paper for the Cambridge International A-levels. As you know, in this restructured format, I don't know why I'm so obsessed with that line there. But anyway, now that that's done, in this restructured format, I don't show question paper. I will assume that you would know where to find your question paper because, I got into problems on my channel previously as a result of showing those copyright content. So yeah, I'm sure you know where to find this particular paper with this particular option code. Before I get started, if you have benefited, if you enjoy the tutorial videos on my channel, don't forget to click the button on the bottom right to subscribe to the channel and turn on notifications when you get new videos. And follow me at ptet.chemistry. That is at ptet.chemistry to get connected, to send in messages, questions, etc. etc. Would love to hear from you. Let's get started. In this question 1, so which one contain the largest number of hydrogen atom? So there are two bits to this question. Largest is something you have to consider, and they are looking at hydrogen atoms. Atoms is something you would have to consider as well. Okay, so looking at option A, I have 0.10 mole of pentane. Pentane is this C5H12. I've started out by drawing skeletal formula because usually organic chemistry doesn't kick in until the later bit of the paper. But if you have watched my other tutorial before, you know I'm a big fan of skeletal formula. It's elegant, it's beautiful, it's simplified. Okay, carbon form 4 bonds. So carbon here form 1 bond because it's bonded to carbon. We don't show the hydrogen bonded to carbon, so there's 3 other hydrogen. Carbon form 4 bond, so I show 2 bond here bonding to carbon, so there's 2 hydrogen there. Carbon form 4 bond, so there's 2 hydrogen there. Carbon form 4 bond, so there's 2 hydrogen there. Carbon form 4 bond, you only show forming 1 bond, so there's 3 hydrogen there. Or you could write the structural formula, CH3, CH2, CH2, CH3. You should be able to interchangeably exchange between all these format, molecular formula, structural formula, skeletal formula. The one thing I really don't want to do is display formula because there'll be a lot of time being wasted. Anyway, in one molecule of these, you have 12 hydrogen atoms. So when you have 0.10 mole of it, then you would have 12 times 0.10 mole of hydrogen atoms. You will get 1.20 mole hydrogen atoms. Okay, we do that for the rest of the options. 0.20 mole of but2ene. But2ene is this, or it could be the cis where they're on the same side, or it could be the trans. It doesn't matter. So they are both CH3, CH, CH, CH3. They are C4H8. The molecular formula is the most important thing in this question, really. So in one molecule of it, there are 8 hydrogen atoms. In 1 mole of it, you have 8 mole of hydrogen atoms. So in 0.20 mole of but2ene, you have 8 times 0.20 and you get 1.60 mole hydrogen atoms. So we are focused on the hydrogen atoms, but first of all we look at the molecular formula. We look at hydrogen molecule for the next one. They are looking for 1.00 mole. So in 1 mole of these, there are 2 hydrogen atoms. So we just have 2 mole of hydrogen atoms in 1 mole of H2. And in part D, they have given us the exact number of hydrogen atoms. So that is the actual number of hydrogen atoms divided by the Avogadro constant, and you will get 1 mole hydrogen atom. So what I've done really is I have converted all of these into mole rather than working out in terms of the actual number of hydrogen atoms. If I had decided to work on the actual number of hydrogen atoms, I wouldn't have converted D into mole. The reason why I want to work with mole is because the rest of the options, 3 of the options are given to us in mole. Only 1 of the options are given to us in terms of the actual number of hydrogen atoms. 3:1. I would say the easiest thing really is to convert into mole, much nicer and easier number to look at. The larger the mole of hydrogen atoms, the larger the number of hydrogen atom, because what you have is the number of atoms, the number of hydrogen atoms is equal to the mole of the atoms multiplied by Avogadro constant. So what we have here is we're looking at which one is the highest number of mole, And looking at all the 4 options, I can say C has the highest number of mole with 2 mole of hydrogen atom, and therefore they will give me the largest number of hydrogen atom. So the answer there must be C. On to question 2. In which pair of species do both species have one unpaired p electron? One unpaired p electron. So that means we are looking at filling in the p subshell. So this means in the p subshell, or you can think about they are in the p orbital. So subshell and orbitals are not the same thing, obviously, but if they're the collection of the orbitals in the same p subshell, they are the p orbitals. And very importantly, they are looking at one there. Okay, should probably choose a color which is a much better thing on the eye. Let's have a look at option A. Option A has argon plus and also C minus. Argon started out as 1s2, 2s2, 2p6, 3s2, 3p6. That is argon atom, but a plus 1 means you have lost 1 electron. So you have lost 1 electrons. So that means I don't have 3p6, I have 3p5. If I have 3p5, I can draw 1, 2, 3, 4, 5. I have 1 unpaired electron. Okay, but it say in which pair of species do both species? You want both species both have 1 unpaired p electron. So I also have to check for C minus. Carbon is 1s2, 2s2, 2p2 because period 2 group 4. But then a minus 1 charge mean gain 1 electron. So it won't be 2p2, but instead it will be 2p3. When you have 2p3, you have 1, 2, and 3. And this is 3 unpaired electrons in the p orbitals. Well, actually in the p subshell, sorry, because each of these is an orbital, so there is 1 unpaired electrons in this orbital, but altogether there are 3 unpaired electrons in the p subshell. Okay, so just to be careful with the terminology there. So that means A cannot be our answer because not both of them satisfy the requirement. If I look at boron, there's 1s2, 2s2, 2p1. You are a second period element, so you are in the second shell, but you are a group 13, meaning to say there are 3 outer shell electrons, 2 in the S, 1 in the P, altogether 2 plus 1 is 3 outer shell electrons. And then you have titanium plus. If I look at titanium first, there's, I can't be bothered to write everything from scratch, but let's just do argon. After argon, then you go to the 4th shell, so there's 4s2, 3d2. This is for the titanium atom. What you have here is titanium plus 1. You have lost 1 electron. So I will fill 4s before 3d, but I will also lose from 4s before 3d, then I lose from the 4s2, and I could get 4s1, 3d2. I can tell you the answer cannot be B straight away because of the titanium thing. Okay, if you look at that, there are no p orbital there, whereas your p orbital is fully filled. Your p orbital is fully filled, so that means you don't have any unpaired electrons in the p orbital. These are not p orbitals, therefore I can cross out B straight away. Looking at option C, I have fluorine and gallium. Fluorine atom is 1s2, 2s2, 2p5. So 2p5, I have 5 electrons there. 1, 2, 3 unpaired, and then pair the 4th one, pair the 5th one, you have 1 electrons in the p orbitals. Boron is a group 13, and from group 13, I can tell you it's got p1 without caring too much about, you know, what shell or whatever, but it's a group 13, it's got to be p1. When you look at the periodic table, you have got like 6 thing there. So this is 13, 14, 15, 16, 17, 18. So the way to look at it is this is actually P1, P2, P3, P4, P5, and then this is P6. So all these things are called the P block. And the reason why you have 6 elements in there is because you have 3 orbitals, each of which can fit 2 electrons, so 2, 4, 6. Of course, you fill parallel spin before you pair them up, but altogether you have 6 elements because you can fill 6 electrons in the P block, in the P orbitals. Group 13, this is P1, definitely you have 1 electrons in the P subshell, which is unpaired in the P subshell. Only 1, both of them, only 1 electrons. they are unpaired in the p subshell. Okay, I'll very quickly show you why D cannot be the answer, but in the real thing, obviously once you get to the answer, you can just move on, and there's the idea there. So selenium, you look at selenium atom is a group 6. When you come to things like this, you no longer consider, the full electronic configuration, you use the group number to your fullest advantage. Group 6 would means it's group, you don't use Roman numeral in the A level, you use group 16. So group 16 is actually P4, something P4, but then it has a -1 charge, so you gain 1 electron. When you gain 1 electron, you become P5, something P5 would mean 1, 2, 3, 4, and 5. So yes, you have an unpaired electron there. We knew our answer was this one already, so I mean, you should know the next bit is definitely wrong, but let's have a look at it. Silicon atom, if I want, I can write down the configuration, but let's just do the shortcut. So it's a group 14. Group 14 is P2, this is group 13, and 14, this is P2. And P2 having gained 1 electron, then it's going to be P3, which means 1, 2, and 3. You have 1, 2, and 3. You have got 3 unpaired electrons. Not both of them have 1 unpaired p electrons. Okay? On to the next question, question 3. So we have phosphorus forming 2 chlorides. So we have PCl3, which is a covalent liquid. That's what they have told us. And we have PCl5. They told us is ionic, and they told us it's ionic solid. And they told us that one of the ion is PCl4 plus, and then they don't tell us the anion. The cation has to balance out the charge on the anion. If you have PCl4 and this is PCl5, you can speculate and suggest that there is going to be Cl minus. However, that's not the question here. The question here is asking you on shape of molecule. So PCl3 is going to be covalent like this. So this is the 3-dimensional diagram showing the 3-dimensional shape. It has got 1 sigma, 2 sigma, and 3 sigma. You count a sigma bond, meaning 3 bond pair of electrons, and you have 1 lone pair of electrons. This is called valence shell electron pair repulsion theory. And you know bond pair, lone pair, repel more. Oops, I don't know why that goes to highlighter. Repel more than bond pair, bond pair. So these are bond pair, bond pair. These are bond pair and lone pair repulsion. They repel more. Therefore, you get trigonal pyramidal geometry. Just like in ammonia molecule, this is going to be 107 degree, where that is 107 degree. On the other hand, you have PCl4 plus, which of course is not the entire PCl5. So just looking at PCl4. PCl4 plus, you can imagine, is it uses the lone pair here to pick up a Cl4. To pick up a Cl plus. What am I talking about? So what it does is it's a dative covalent bond, just like ammonia molecule NH3 pick up a H plus. Here it pick up a Cl plus. The charge get transferred to the phosphorus. Now what you have is a dative covalent bond, but it's still a sigma bond. So you have 1 sigma, 2 sigma, 3 sigma, and 4 sigma. 4 sigma would mean 4 bond pair of electrons, but you have no more lone pair of electrons, so there's 0 lone pair of electrons. In your valence shell electron pair repulsion theory, you say the 4 bond pair repel equally, and when the 4 bond pair repel equally, the geometry you get is called tetrahedral, and that will be 109 degree, where any of these bond angle you look at, they are 109 degree in 3 dimension. These are flat in the screen. If you are watching this on the screen, presumably they are flat on the paper. This is coming up towards you, pointing at you, coming up from the paper, from the screen. This is pointing away from you, behind the screen. Okay, so that's tetrahedral. This is trigonal pyramidal. So we're looking at option B here. That's the answer. Looking at question 4, it looks like a classic enthalpy change of reaction question. So what we have here is an equation for combustion. Combustion of methane, complete combustion of methane would give us carbon dioxide and also water. Of course, you need to balance the equation. This topic is about enthalpy change. Everything need to have balanced equation because the stoichiometry, the mole matters. Now what we have here is, this is what you want to find. Okay, what to find. So you can find more about this from the A-level concept tutorial playlist. I've got a couple of videos there that I never deleted prior to this copyright stuff, so you can still view those in your own time and find out more on how I explain these particular techniques that I'm going to use. Okay, so what have been given is delta H1, which is the formation of methane. But on the other hand, they give us the combustion. They give us the combustion of carbon. They also give us the combustion of hydrogen. Ideally speaking, what they want us to find is combustion. They have given us this formation, but they have not given us the formation of these and these. But of course, I remember that carbon plus O2 give me CO2. So there's gas, there's solid, and there's gas. This thing is also equal to the formation of CO2. So just because they've given us this combustion of carbon, but combustion of carbon is exactly equal to formation of CO2. These are identities, which, as I mentioned, you can find out more on how I explain this in the A-level concept tutorials on finding out more about energetics, okay, AS energetics. You are burning 1 mole of the substance in excess oxygen. You're also forming 1 mole of the substance from its elements in its standard state under standard condition. Onto the hydrogen one, it's a similar concept. If I burn 1 mole of hydrogen gas in excess oxygen, I'll get H2O in a standard state. Of course, then I need to balance the equation with a half there, because when I burn 1 mole of H2, it only burns with half mole of O2. Whereas when I form 1 mole, well, in fact not whereas, it's also the same thing. When I form 1 mole of H2O, I also form it from 1 mole of H2 and half mole of O2 in their standard states. So that is also the formation of H2O. So what we're saying is delta H2 is also the formation of carbon, and delta H3 is also the formation of H2. What am I talking about? The formation of CO2 and the formation of H2O there. Okay, so ultimately what I can do is I can write in delta HF formation. So that is delta H1. This is going to be 0 because this is element. The enthalpy of formation of any element is 0. Enthalpy of formation of CO2 is the same as enthalpy of combustion of carbon. So there's going to be enthalpy 2, and this is enthalpy 3. Remember this equation, you are forming 1 mole of H2O. I've written down enthalpy of formation here. This is forming 1 mole of H2O. That was why I said the mole ratio really matters. Therefore, when you want to find the enthalpy change of reaction, in this case, the reaction happens to be combustion, but the data you have, this is the data given. The formula you use is always depending on the data that you are given. So since you have been given formation, so it's the enthalpy of formation of product minus the enthalpy of formation of your reactants. Okay, so a lot of students, they always just write product minus reactant, and that is wrong, because you got to remember there is the formation of the product minus the formation of the reactant. This is the sum of it because it depends on the number of mole. So here the product, you have 1 times that, so it's 1 times delta H2, and then you have plus 2 times delta H3. So that is your enthalpy of formation of your products minus the enthalpy of formation of the reactants. So it's 1 time delta H1. So looking at the option given, so that is corresponding to 1 of H2 plus 2 of H3 minus 1 of H1. So this is equal to option D there. Question 5 is about Boltzmann distribution. So that is a very popular question related to rate of reaction. So we have X here, and we are given this is Y, and we are shown 2 things. We are shown one thing that looks like this, and then the other graph that looks a bit like that. Okay, so we are told that this is T1 and this is T2. So this is my own graph. I drew this graph. So this graph was not copyrighted from anyone. Everyone else have seen Boltzmann distribution, obviously, as a chemistry student. So, you know, I am just referring to the question paper, which of course I'm not showing here. So be very careful if you think I violated any copyright issues. All right, so let me know. What is plotted on the y-axis and what is on the x-axis? The x-axis is actually energy, and this is where you will label activation energy. That's why activation energy is on the x-axis. Y is the number of particles with energy E. So it's the number of reacting particles or reacting molecules with energy E. What happened is at the higher temperature, more particles will have higher energy, they will move at faster speed. So going from T1 to T2, the temperature is actually higher. So T2 is higher temperature than T1. And then on the y-axis, there's going to be the number of molecules. So we're looking at option B there, where T2 is the higher temperature. That's why the whole graph shifts to the right. And in return, you have greater area under the graph because you have more molecules that have enough energy to react. That's why faster rate of reaction at the higher temperature. That's T2. And on the y-axis, there's the number of particles or the number of molecules with that particular energy E. So option B is the correct answer there. Question 6. So this is a calculation question, something to do with stoichiometry. They're talking about complete combustion. So there's two things here. Complete combustion of propane. So propane is an alkane. So it's CnH2n plus 2 from your IGCSE or O-level chemistry. So C3H8. Or I can draw the skeletal formula, or I can write the structural formula. Of course, you're more than accustomed to these things by now. If you're not, then you should really get prepared for this instead of doing the display formula. So I'll just use the molecular formula for writing the balance equation to do combustion. Complete combustion means I get CO2 and H2O. 3 carbon means I get 3 CO2. 8 hydrogen means I get 4 H2O because 4 times 2 is 8. So ultimately, I need to balance the oxygen. 3 times 2 is 6 oxygen. 4 times 1 is 4 oxygen. 6 plus 4 is 10 oxygen. I need 10 oxygen atoms. I have 2 here from the molecule, so I need 5 there. Okay. As a matter of fact, this equation must be balanced since they do require us to use something to do with the oxygen. So this is what they want us to find. They want the mass of O2. And they have given us the volume of propane. This is 12 dm cube. So this is volume of the gas. Okay. So what happened then is I want to set up my mole ratio. If you have watched any of my other tutorial videos on mole calculation and stoichiometry, provided you watched them before they got deleted. And of course, there's also those A-level concept tutorial playlists which contain a lot more of these mole calculation setup, which I explain how to set them up if you don't understand this particular method that I'm showing you here. So I set up by writing, by labeling what the mole of something I want to find and the something else that I'm given. There could be the other way around. It does not matter because I'll show you that it's just rearranging equation, something that you learn in algebra from primary school as well as lower secondary and upper secondary mathematics. This is equal to whatever it is from the balance equation. So I've got oxygen on top. I should write down 5 here because I've got 5 from the balance equation. This means 5 mole of oxygen reacts with 1 mole of C3H8 from the balance equation. And that is equal to the actual mole that reacted. I want the mass of oxygen. So if I have mass, I will use mass over mR. And the mR of O2 is going to be 16.0 times 2 from your periodic table. Your calculator will show you 32, but you know better because you use 16.0. Your mR is actually 32.0, just saying. So I label everything, the mass of O2 divided by 32.0. That is the actual mole of O2 that reacted. At the bottom, there's 12 dm cube. It's the volume of gas. So I'm talking about volume of gas divided by the molar volume of gas, of which it is 24.0 dm cube per mole. This means 1 mole of any gas, occupies a volume of 24.0 dm cube. So 12 dm cube divided by 24.0 dm cube per mole will give me the actual mole of the C3H8. As I promised, it's just all about rearranging equation. So, you need to be very good at doing this mathematically speaking. And of course, you can skip the step if you know what you're doing already. I'm just showing this to cater to learners of every single ability. press that into your calculator. So I'm still using my good old friend for 20 plus years already. That's because I know my calculator very well. Even though all the letters have come off and stuff, I still like it very much because that's my calculator. Okay, option B there, that's the correct answer as I've gotten and shown you there. Question 7, so this is about first ionization energy, and they're asking us oxygen versus nitrogen, first ionization energy. If I'm doing this, I need to think about the group number. Oxygen is group 16, nitrogen is group 15. I need to think about the electronic configuration, 1s2, 2s2, 2p4, 1s2, 2s2, 2p3. I just focus on 2p3 versus 2p4. I hope you can see this now. 1, 2, 3, parallel spin first, but I've got 4 electrons. So I've got 2p4, so 1, 2, 3, and then the fourth one has to be paired. Whereas in nitrogen, it's just p3. So what do we see here? We see that this paired electron, whereas these are all unpaired electron. So the difference between the paired electron versus the unpaired electron is the paired electron repel more than unpaired electrons. As you could imagine, electrons and electrons are negatively charged, so they do repel each other. But here, at least they are occupying their own orbitals. The respective orbitals point in each direction, so they have different directions. But here, in the same direction, meaning to say the orbitals in the same orbital, they point in the same direction. There are 2 electrons that you're trying to accommodate in the same space. They repel more. Because they repel more, so it's unfavorable, therefore easier to remove. If it is easier to remove this particular electron, therefore slightly lower first ionization energy. As you will know, because you know how to sketch out the first ionization energy trend across a period, it goes up, it comes down, it goes up, it comes down, it goes up, and it comes all the way down. Okay, so that is a result of new groups. So there's like group 1, there's 1, this 2 to 13. So the first drop is due to S versus the P subshell, whereas the second drop here, this is P3 and this is P4. So this thing is to do with P3 versus P4, which is to do with this paired electron repelling more than the unpaired electron. Very, very popular structured question actually. So we are looking at option C. Option C is the answer, basically encapsulate everything that I have just explained just now. Question 8. So this is about ideal gas. So ideal gases or gases are most ideal when we have low pressure. That means you don't squeeze the particle close together. They are very far apart, and therefore that they are as ideal as possible. And also at high temperature, when the particles travel at high speed and they have a lot of energy to move further away from each other, and therefore since they are not very close to each other, they are more ideal than expected. When you look at helium, nitrogen, ammonia, and krypton, so I can think that krypton is going to be, well, first of all, the question is most ideal. They want which one is the most ideal, and something you should circle or underline your question. NH3 is going to be out of the question because they have hydrogen bonds between the molecules. These are very strong intermolecular forces that will violate one of the requirements for ideal gas, which is negligible. Sorry, one of the assumptions for ideal gas, which is negligible intermolecular force. So I can cross out option C there. Between krypton, helium, and nitrogen, I can cross out krypton because too many electrons. Too many electrons, strong van der Waals. Van der Waals forces of attraction depends on the total number of electrons, which krypton has a lot compared to helium and nitrogen. And again, between helium and nitrogen, helium only has, not 4, but 2 electrons because it has 2 protons. And nitrogen molecule, each nitrogen has 7 protons, so 2 nitrogen atoms. Did I say each nitrogen molecule? Sorry, each nitrogen atom has 7 protons. So there are 2 nitrogen atoms in this molecule. So there are 14 protons and therefore 14 electrons total. Between this and this, helium is weaker van der Waals forces, Weaker van der Waals would mean more negligible intermolecular forces. That's why B cannot be the answer. A has to be the most ideal gas out of all these four. Question 9 is about oxidation number. So what do we have here? We are given this equation, which is a classic redox equation for what happened when corn sulfuric acid reacts with hydrogen iodide. So the sulfur, let's have a look at this question first. They want the change in oxidation number. Be very careful. The change in oxidation number means final oxidation number minus the initial oxidation number. So let's have a look at the individual oxidation number. First of all, this is Hi, so the iodine is going to be -1 because the hydrogen there is +1. When you look at oxidation number, you just look at the species and you don't care about the number in front. So the hydrogen in the compound is +1. The overall compound has no charge, and therefore the iodine there is -1. Oxidation number +1, there's only one of it. -1, there's only one of it. Together, they give you this compound, this molecule, which have 0 oxidation number. H2SO4, the overall thing is 0 charge, 0 oxidation number. There are 2 hydrogen, and there's 1 sulfur. There are 4 oxygen, each of which is -2. So the sulfur there is going to be +6. Okay. In H2S, what you have is 0 overall oxidation number for this molecule. There are 2 hydrogen, each of which is +1, and there's 1 sulfur. Sulfur there is -2. Based on the general rule that hydrogen is always +1 in a compound, most likely. Oxygen is mostly -2 in compounds. Such as in this water, hydrogen is +1, there are 2 of them. Oxygen is -2, there's 1 of them. The molecule itself has no charge. Iodine as an element, so this is iodine as an element, is going to have 0 oxidation number because it's bonded to itself, So what we can see is iodine -1 to iodine 0. So this is an increase of how many? Increase of 1, so meaning to say it's +1. If I then do the sulfur +6 going to sulfur -2. So this is a decrease, and this is the one you need to be very careful. Final minus initial, so this is a decrease of 8. So what we can see is iodine has an increase of 1, so there's going to be C or D. But then this is a decrease of 8, and a lot of students couldn't do this correctly. Final minus initial, don't forget that. And you're going to get -8, so there's going to be option D there. Okay, so option C is incorrect, option D is correct there. Looking at question 10, question 10 is about Haber process, whatever you like to call it. You have a heat exchanger, so what are we looking at? So the N2 and 3H2 goes in, and then you have the heat exchanger. I'm just very quickly drawing this diagram, and then you have passing it through catalytic converter, and then it passes it back into here, so it goes there and then goes there, and then that goes out to condenser. So this is a condenser. What the condenser does is it condenses the NH3 gas into liquid ammonia, which you can then collect, and then this is unreacted N2, and H2 will go back and be recycled as your reactant. So what's the purpose of the heat exchanger? So you want to cool the incoming gas mixture to avoid overheating the catalyst. A is completely bollocks, so that doesn't quite work. So this is to heat up the gas to a certain temperature, but then you also need to cool down the gas because there's the condenser there as well. So the condenser is the one responsible for cooling it down, not the heat exchanger. Okay, so the heat exchanger is not used for cooling because this condenser is used for cooling. So perhaps I can say that for cooling what? For cooling NH3 gas to NH3 liquid, and we collect NH3 liquid, and as you collect the NH3 liquid, the equilibrium will try and produce more ammonia to try and replace the ammonia in that dynamic equilibrium. So A is wrong because of that word cool. All right. B, to cool the reaction products and separate the ammonia. That is also wrong. Again, they say cool the reaction products. They say cool the ammonia. That is not correct. That is the purpose of the condenser. So as I mentioned previously, condenser was the one that will condense by cooling the NH3 gas to the NH3 liquid. So you're looking at option C and option D now. So they say to warm the incoming gas mixture. So C and D both are warming. So that is correct. But then C mentioned something about shift the equilibrium, give more NH3, give more NH3. More NH3 is definitely wrong because as you know, N2 plus 3H2 equilibrium to give you 2 NH3. The forward reaction is exothermic, meaning to say it's negative there, therefore it releases heat to the environment, to the surrounding. When you increase temperature, the heat exchanger warm up the gas. When you increase temperature, this equilibrium will try to decrease temperature by releasing less heat. When you release less heat, you don't produce more product because the forward reaction is exothermic. So you will go backward and it will give you less NH3 when you heat up the system. So C is wrong, which means D must be the correct answer. Of course, we know that D warms up the gas mixture and is to do with rate. So rate is the key concept here because as you know, you don't want too low of a temperature as that would mean that the forward reaction would be very slow. But you can't go too high of a temperature because that will mean a very low yield of the NH3 based on what we just explained in terms of Le Chatelier principle. So D is the correct answer there. Be very careful about this concept called rate versus equilibrium. You can find out more in my A-level tutorial playlist. There are a couple of videos on rate versus equilibrium which I never deleted back then. Okay. So moving on to question 11. So which statement about catalyst is correct? So one thing you need to be aware of is catalyst. A lot of students they have this misconception about catalyst. So I'm just gonna draw energy profile diagram. So this is reaction coordinate or reaction progress, whatever you want to call it. I'm just gonna draw for exothermic reaction, for instance. So from the reactant to the product, so the enthalpy change there is less than 0. Activation energy is always drawn from the start to the top of the peak. From the start to the top of the peak. It's not as a double-headed arrow. And then obviously when you have catalyzed reaction, then you will have a slightly different activation energy. So from the start to the top of the new peak. So nope, I don't want that. Let me just see if I can draw a bit better. So this is going to be EA catalyzed. So we can see the EA catalyzed is lower in energy than EA, well, uncatalyzed. But anyway, so as a result of that lower activation energy, then the reaction happens a bit faster. What people don't understand is that on the Maxwell-Boltzmann distribution diagram, whether you use a catalyst or not, so on the Maxwell-Boltzmann distribution diagram, same like in the earlier question when they ask you on Maxwell-Boltzmann, on the y-axis is the number of molecules with energy E. This is energy E. So if I just draw a distribution like this, and then I will have activation energy, no catalyst. And then what happened then is, well, I should probably use the same color just to avoid confusion. When there is a catalyzed reaction, I'll get EA catalyzed. So there is a greater area under the graph because there's a greater proportion of molecules with enough energy to react. So just now you have just the pink area. Now in addition to the pink area, you have the green area as well. So you have increased the proportion of molecules with energy greater than or equal to EA. And that is why there are more particles with enough energy to react. And that is why option C is actually the correct answer here. Now they have taught you something back in IGCSE or O-level chemistry. They said that catalysts lower activation energy. That is not exactly correct. They offer alternative reaction pathway. You will learn more about this in A2 as part of catalysis essay in A2 rate of reaction. Alternative mean optional reaction pathway, and this optional reaction pathway have new lower activation energy. And it is this new lower activation energy that means that there are more particles or more reacting molecules with energy greater than or equal to the new lower EA, and it is a result of this that you get greater proportion or greater percentage of this thing, or what we call effective collision, and as a result of that, rate would increase. So there was option C here, and these are the kind of thing they will expect you to be able to do in a structured paper. I'll very quickly go through the options why A is wrong. A is wrong because of increasing activation energy. So obviously you don't want the activation energy to increase based on what I said earlier. You want the activation energy to be new and lower. Now they increase the rate of reaction by lowering enthalpy change. So B is wrong because of that word there, lowering enthalpy change. So they don't change enthalpy change at all. Because as you saw from this reaction profile diagram, that the enthalpy change doesn't change whether you have catalyzed or uncatalyzed reaction. Enthalpy change is independent of that rate of reaction or change in activation energy. Option C is our answer. Option D is incorrect because of same. Okay, so it should be different there because it's to do with heterogeneous. Hetero refers to different. Okay, so D is a wrong definition for heterogeneous catalyst there, as stated in the syllabus under AS rate of reaction. Question 12. So this looks like descriptive inorganic chemistry. What is this? This looks a bit complicated. X is period 3. X can form a solid oxide, so X plus O2 giving you Y. So this is a solid oxide of period 3. What else can I tell you? So if it is a solid oxide, I can tell you straight away it is not SO2, SO3, so not sulfur. We are looking at P electrons. So if you look at the options, not really. What can I say? Let's see. Y reacts with hot concentrated hydrochloric acid. Okay, I think I get it now. Y is an oxide of period 3. It can react with acid. It can react with HCl. It can react with NaOH. Now this is a big thing because this means it can react with both acid and also base. So that makes it amphoteric. Is that how you spell amphoteric? I think I spelled it incorrectly. Amphoteric. Let me just spell that again. Amphoteric. So it's an amphoteric oxide. It can react with both acid and also base. And therefore, we're looking at Al2O3 in period 3. If there is Al2O3, so there's the oxide Y. Therefore, X must be aluminium. And if X is aluminium, we're looking at 1s2, 2s2, 2p6, 3s2, 3p1. Okay, so it's group 13. How many p electron does one atom of X have in the outer shell? So we're looking at option B here. Okay. Question 13, we have a mixture of calcium hydroxide. So calcium hydroxide is a base, so it's got OH minus, and then you pass it with ammonium chloride, ammonium ion, NH4 plus. So this is your classic displacement of ammonia. So this is a H plus acceptor, whereas the NH4 plus is a H plus donor. So this is your acid and this is your base. what will happen is the OH minus accept the H plus and you get H2O. The NH4 plus loses the H plus and you get NH3. This is your classic ionic equation that even I teach year 9. So these are year 9 ionic equation on what happened regarding the displacement of ammonia when you have ammonium ions reacting with any base, which is any hydroxide ion, any alkali. This is your paper 3 production of ammonia, which you test with red litmus paper, and it will go from red to blue. So on the full balance equation, you will have, you will have salt, which is going to be calcium chloride. So CaCl2 because calcium group 2, Ca2 plus, chlorine group 17, Cl minus. So CaCl2, and of course you get H2O and NH3. I have 2 chlorine there, so 2 NH4Cl. If I have 2 NH4, I'll get 2 NH3. And if I have 2 OH minus there, I'll get 2 water. As you could imagine, 1 OH minus accept 1 H plus. If you have 2 NH4 plus, you need 2 OH minus to accept 2 H plus to give you 2 H2O. So this equation is nice and balanced. The gaseous products. So the gaseous products, they say gaseous products. So not just NH3, H2O is typically liquid, but they say gaseous products. This can't be gaseous product because that is an ionic solid. It doesn't easily turn into a gas at all, whereas at least this turns to gas at 100 degrees Celsius. So your gaseous products are going to be that. So what can I say? Your gaseous products, H2O and NH3 passes through solid calcium oxide. So H2O plus calcium oxide, you're going to get calcium hydroxide back again because this is a basic oxide. When they react or dissolve in water, they give you an alkali or a base where the pH is above 7. On the other hand, you have H2O plus NH3, so there's no reaction there. Well, there is a reaction actually, NH4 plus and also OH minus, which of course is in equilibrium with NH3 aqueous, and that is going to be your weak base. That is your weak base. This is also a weak base actually, but this is ammonium hydroxide, which is in equilibrium with NH3 when NH3 dissolves in water. A single gaseous product is collected. That is because this thing is not very soluble. So this thing is not very soluble. So a single gaseous product is collected. What am I talking about? What am I talking about? Calcium oxide. Calcium oxide will react with water, yes. But calcium oxide, first of all, is a basic oxide. What am I talking about? This is NH3 with water. No, that's not what I want. I want the NH3 reacting with calcium oxide. I beg your pardon. I want the NH3 reacting with calcium oxide. So calcium oxide is a basic oxide. And this is a base. So there is no reaction. So I will get the NH3 as a gas, still get NH3 as a gas, and this NH3 is W. W is going to be NH3. NH3 reacts with Cl2, NH3 plus Cl2, I get 2 gases, X which is element, and I get Y which is acidic. I guess when you think about acid and this is a base. The acid I can be thinking about is HCl, so that one should be quite obvious. If there is HCl, so the H and the Cl combined, and this is an element, so all the hydrogen goes to the chlorine, which means the element I'm going to get is going to be nitrogen as an element. It's a molecule, N2, so X must be N2, and Z must be HCl. No, Y is HCl, but then HCl can react with NH3. HCl is Y plus NH3. That can give you NH4Cl, which is Z, because that is going to be your acid, that is going to be your base, this is going to be your salt, and this is just your neutralization reaction. Okay. Oh, looking at all that, I have gotten my Z to be NH4Cl. I've gotten my X to be N2. So of course the question can change to ask you on why as well. So looking at that, I'm looking at N2 and NH4Cl. So there's option B as my final answer there. Question 14. So, what am I doing? Question 14. So this is group 2 chemistry. So Q is a mixture of group 2 oxide, which I shall call it QO because it's Q2 plus and O2 minus, and also group 2 sulfate, QSO4, so Q plus, 2 plus because group 4, it's a group 2 ion, so Q2 plus and SO4 2 minus. It's a group 2 ion, Q2 plus and O2 minus ion. And this is equal amount, 1 is to, equal amount. I was about to say equal 1 mole is to 1 mole, but they say equal amount. So we need to be careful here. So Q is shaken with water and you filter it. So QO and QSO4, you plus water, then you filter. After you filter, then you're gonna get residue and you're gonna get the filtrate. Filtrate is the one that passes through the filter paper. Residue is the one that remains on the filter paper. When this solid residue is shaken with HCl, no reaction. But this thing, the filtrate, you plus H2SO4, you get a white precipitate. So we are introducing sulfate ion, and the test for sulfate ions is using barium. So this white precipitate is barium sulfate. The sulfate come from here, but the barium must have come from the filtrate. So we're looking at Ba2 plus aqueous. Filtrate means it's a aqueous solution because it passes through the thing. So what could be Q? Q must contain barium. So the barium must be there because nothing has changed. So there must be barium. And it's a mixture of group 2 oxide. Oh, I beg your pardon. They say group 2 oxide and group 2 sulfate. They don't tell you that they are the same. They don't tell you they are the exact same thing. They just say group 2 oxide and group 2 sulfate. So they don't tell you they are exactly the same. So we cannot assume they are exactly the same. What I can be sure about is the sulfate there give you the barium sulfate, so there must be barium. The question is, do we have barium oxide or do we have barium sulfate? Let's see. If we have barium sulfate, when we filter it, then the filtrate will not contain barium sulfate because barium sulfate is insoluble. So that's the logic behind it. When you filter it, how can you get Ba2 plus in here to give you barium sulfate? It's because Ba2 plus is in here. That means your barium sulfate cannot be present there, which means A and C must be out. Because if barium sulfate is here, when you filter it, barium sulfate will be in the residue. You will not get any barium here to give you barium sulfate later on. Okay, so Q is this mixture here. So A and C is out. I'm left between B and D. So now between B and D, this thing will react, no reaction with HCl. HCl is an acid. So what will not react with acid? If you have barium oxide will give you barium hydroxide. This is very soluble because it's pH 14 in solution, so which means it's a strong base. It's going to react with the acid, but this residue must be magnesium hydroxide because the magnesium oxide can dissolve in water to give you magnesium hydroxide, which is not very soluble, whereas barium hydroxide is very soluble, which means this one cannot be barium. This one has to be magnesium hydroxide, which doesn't want to react with the HCl because it's not very soluble. So it means we also have magnesium oxide there, so which means we are looking at magnesium oxide as well as barium oxide and magnesium sulfate. So the magnesium sulfate, if we have barium oxide, which is very soluble, so barium oxide is the one that is very soluble. Barium oxide, let me just restart that again. Barium oxide plus water will give you barium hydroxide, very soluble, pH 14, very strong base, which means if I want the barium in the solution, I'm looking at option A or B, which means C and D is out, because that doesn't give me very soluble hydroxide. Magnesium hydroxide is not very soluble. Between A and B, as I mentioned, I want to get barium sulfate as my final precipitate there. Therefore, I cannot have barium sulfate there. If I have magnesium A and B, if I have barium sulfate there, if I have magnesium sulfate will give me magnesium hydroxide. Magnesium hydroxide will still react a little bit with HCl. I beg your pardon. Magnesium hydroxide is still alkaline. This is still alkaline or basic, which means it will still react with acid. But here no reaction would means totally no reaction, which means we must have barium sulfate as well. Yeah, we are looking at barium sulfate as well as barium oxide. Barium sulfate and barium oxide. That's going to be option A here and not B. Okay, because if it is B, then you will get magnesium hydroxide as the magnesium sulfate, a little bit of it dissolved in water, and you will get this thing which will react with acid. But when you have barium sulfate totally, it will not react with the acid at all. Okay. Moving to the next question, question 15. So this is thermal decomposition. What is key is we have hydrated. Hydrated means has water of crystallization. So MgNO3 twice, because there's Mg2 plus, NO3 minus. And then it's got certain number of water crystallization, which I don't know on top of my head. But what I'll get first of all is I will get the H2O and then the MgNO3 twice, because this is gentle heating. And you will see colorless liquid form on the upper side of the tube as it condenses on the cooler part of the tube. And then as you heat it further, the magnesium nitrate can decompose further, and that will give you the group 2 oxide, and then the nitrogen dioxide, as well as half mole of oxygen gas. I've done this a lot of times. That's how I know they are balanced this way, because 2 NO3 give me 2 NO2, 4 oxygen, 1 oxygen, 5 oxygen. I want 6 oxygen, so I have half of oxygen molecule. So you can get steam because you're heating it very, very strongly. That will condense on the upper part of the tube and give you liquid water again on the upper part of the tube. And you will get magnesium oxide. So this is magnesium oxide. This is oxygen gas. This is called nitrogen monoxide. Sometimes the other name is given as nitrogen 4 oxide, because the nitrogen there is +4 oxidation state, but the other name cannot be dinitrogen monoxide. Dinitrogen monoxide is the other way around. It means there are 2 nitrogen and 1 oxygen, and this is not going to be the product, because they say will not be the product. So A is the answer that we are looking for here. Question 16, what looks like a calculation is not actually calculation. So, looks complicated actually. So 5 cm cube, 0.05 molar. Molar in capital M stand for mole per dm cube NaCl. You mix that with 5 cm cube, 0.05 molar Ki. And so you mix that together, and then you add in 10 cm cube. Okay, I think all this information on the volume actually is useless, because what is important is you're going to get precipitate. So you're going to get AgCl plus AgI. This is white precipitate AgCl. This is yellow precipitate of AgI. What happened then is when you add concentrated ammonia, the AgI precipitate remains insoluble. So you will still see yellow precipitate. However, you will then get AgNH3 twice plus, and then Cl minus, because that is the active ingredient in Tollens reagent, and Tollens reagent is colorless to begin with, because AgCl can dissolve in excess ammonia. In fact, you just need dilute ammonia. Here you use concentrated ammonia, so you definitely dissolve the silver chloride in excess ammonia. This is the active ingredient in Tollens reagent, which is colorless. So what you see then is the AgI precipitate, which is going to be the yellow precipitate. So there's option C, which is your answer there. Question 17 is about volatility. So this English word called volatile means boil easily. Someone who is volatile gets angry easily. So their blood pressure literally, boil to the roof when you trigger them or whatever. So they're saying volatility decreases down the group. So they say it becoming easier to boil. So CO2, Br2, and I2. At room temperature and pressure, that is 25 degrees Celsius, 1 atmospheric pressure. Chlorine is a gas, bromine is a liquid, iodine is a solid. So what we can say is becoming more difficult to boil, more difficult to melt or to boil. Therefore, we can say volatility decreases. Okay, and what is responsible for it? Remember that these are all simple molecular structure or simple covalent molecule. When you have simple covalent molecules, when you melt them or when you boil them, you are only breaking the weak intermolecular forces between the molecules. In this case, in air-level studies, you know that these are specifically called van der Waals or induced dipoles, which of course they are non-permanent dipole. Since they are bonded to themselves, these are non-polar. So we don't talk about permanent dipoles, we just have weak van der Waals between the molecules. And as a result of this thing that we are breaking, weak van der Waals, we are looking at total number of electrons in the X2 molecules, in the halogen, increases. So van der Waals is stronger. But there's also another factors which you might not have heard of, which is total surface area. So your halogen are getting bigger and bigger down group 17. Therefore, van der Waals also gets stronger. As a result of these two factors, then your boiling point increases, your melting point increases, your volatility will decrease as a result of that. So looking through the options, bond length and bond strength are absolutely wrong because we are not breaking the covalent bond. Electronegativity is absolutely wrong because again, these are all non-polar. We are looking at the total number of electrons in the molecule. In addition to that, in your structure paper, you are supposed to include the idea on surface area as well. Question 18 is about environmental chemistry, acid rain. So acid rain is a dilute solution of sulfuric acid. They talk about carbon monoxide, carbon dioxide, NO2, and unburned hydrocarbon. So unburned hydrocarbon can cause photochemical smoke. It's what happened in big cities with a lot of factories. So this thing can cause breathing problems or respiratory distress or breathing problems, that kind of thing. So CO it has a toxic effect on your hemoglobin of your red blood cell. Carbon dioxide is a greenhouse gas that can cause global warming. So there's quite a lot of issue on the world getting a lot hotter year after year, and that's probably a result of increased human actions, cutting down forests and that kind of stuff. Nitrogen dioxide is definitely the answer we're looking for. So carbon dioxide is weakly acidic, so it doesn't exactly cause your acid rain. CO is what you call a neutral oxide. It really don't want to dissolve in water, and this is non-polar. Despite carbon and hydrogen having different electronegativity, you can imagine that oil doesn't mix with water, hydrocarbon doesn't mix with your rainwater, they're non-polar. Okay, so option C is the answer we are looking for in question 18. Question 19 looks like a calculation question. So R is an oxide of T. So T is a period 3 element. So period 3 chemistry is your big topic in AS chemistry. So 5 gram of R contain 2.50 gram of T. Okay, so this is actually empirical formula. I can tell you the trick to this question is empirical formula, I think. All right, so T is the element. So T is the element, and then this is together with oxygen. Okay, so let's say oxygen atom. So what you have is total you have 5.00 gram. If you have 2.50 gram of the element, and you have, well, the remaining thing will be the oxygen. So you also have 2.50 gram of oxygen. Then what happened then is, this doesn't make sense, does it? Let me see. I think I better just copy this onto a new page because I think I might need quite a lot of space to do this particular thing. They've given us options, so we might have to do try and error on this. So these are the mass as you do your your empirical formula kind of thing. So you do mass, and then you will have mole. Then you will have mole when let me think. So it's 2.50 over 16 because you're talking about simplest ratio of atoms. This is 2.50 over the AR of T. So yeah, let's see this thing. 2.50 divided by 16. So I'm doing this for the first time actually, as the paper just got released. But anyway, let's see what happened here. So obviously we don't have the AR of T, but then they have given us the option. These are the options they have given us. And we have A, which is magnesium. We have B, which is aluminium. C, which is silicon. And D, which is sulfur. 5 gram of R contains 2.0 gram of T. I think I might have overcomplicated this. This is actually a percentage composition question. Scrap that. You see, what happened is when you try and do something without actually thinking about the scenario first, I should have done better there. It's about percentage composition and not empirical formula. So I think I'm mistaken about that. So this is mass composition. It's actually a year 9 topic I've just taught, to be honest. Mass composition. So if you have 5.00 gram of these, and we know about their oxide will be MgO, the oxide will be Al2O3, the oxide will be SiO2. Sulfur form 2 oxide, SO2 and SO3. So let's just check through the other option first. So let's check MgO. So when we have MgO, out of the whole MgO, the relative molecular mass, 24.0 plus 16.0 give me 40.0. Out of the 40.0, there's only one oxygen. There's only one magnesium, so 1 times 24.0 over 40.0 times 5.00 gram. This will give me the mass of the magnesium. So 24 divided by 40 times 5, I get 3.00 gram. This is not 2.50 gram of T, therefore A is not the answer. For B, do the same thing, 27.0. Is it 27.0? I might have gotten this one wrong. Yeah, it's 27.0 times 2 plus 16.0 times 3. I get 102 as the relative molecular mass. I've got 2 times 27.0 because I have 2 aluminium in the whole formula unit times 5 gram. So I was right. This question is about mass composition. So once you unlock the question, there's nothing that can trick you anymore. 2.65 gram to 3 significant figure. Again, this is not 2.50 grams, so B must be wrong as well. On to C, so I have 1 silicon, which is 1 times 28.1 divided by 28.1 plus 16.0 times 2, I get 60.1 times 5 gram. I can pretty much tell that that is not going to work as well. So again, this is not 2.50 gram. So well, try next is, well, pretty much we know the answer is D because none of them works, but let's just try for SO2. So there's 1 times sulfur, which is 1 times 32.1 divided by 32.1 plus 16.0 times 2, I get 64.1 times 5 grams. So I can pretty much see 32 over 64 is half of it. So half of the 5 gram is going to give us 2.50 gram, which is what we want. So D is going to be the answer that we are looking for and not any of the other options. Question 20. So this is the beginning of the organic level questions. So they say bromoethane. This is bromoethane. You react it with cyanide ion, so Cn minus, and you will get propanitrile. So I'm just drawing 1, 2, and 3. I started from 2 carbon, and now I have 3 carbon. So this is called propanitrile. Nitrile is the C triple bond N. It's going to be CH3, CH2, C triple bond N. Cn minus like this. Of course, if you want to balance the equation, it's going to kick out the Br minus like that. And I should really write structural if I want to write that second sentence correctly. What's going to happen is this is SN2 mechanism. SN2 mechanism means, it happened in one step. So the mechanism goes like this. If I draw the mechanism, it will be CH3C. If I display it correctly, then label dipole first of all, delta minus on the halogen. So NC, the lone pair on the carbon, attacks the carbon delta plus, then kick out the CBr. It actually proceeds via the transition state, where it's not a real 5-membered carbon, but it's like a transition state where it has got partial bond here and partial bond there. The rest of them are full bond. This is what you have double dagger, and you have a negative charge because you have a Cn minus plus no charge, you have a -1 charge. Obviously, this bond will get longer and it will break. This bond gets shorter and it will form, and you will get CH3, H, C triple bond N, and you will kick out the Br minus as your leaving group. So which statement about the mechanism is correct? I went through the whole mechanism, so you should be able to, find out which one was correct and not. The first one, A, the lone pair on the electrons, the lone pair of electrons on the carbon of Cn minus attack the lone pair on the carbon, attacks the carbon atom of the CBr. So I'm pretty sure A is the answer we are looking for. Let me just go through the other option and tell you why they are wrong. The lone pair on the electrons, so this is option B, the lone pair of electrons on the carbon of cyanide ion attacks the carbocation. So we don't have carbocation, so B, the carbocation is already wrong because that will indicate SN1, which this reaction tell you is SN2. Option C is wrong because they say lone pair on the nitrogen. We are not forming a nitrogen carbon bond, we are forming a carbon-carbon bond. That's why we get propane nitrile. D is wrong because of carbocation again. So D is wrong because of carbocation again. So pretty much, if you know the mechanism, you can see that A is the only correct answer there. So question 21 is an organic question as well. So we're looking at two different, so there are a couple of key terms to look out for. Two different, and they say carboxylic acid. So this is a result of reacting alkenes with hot concentrated acidified KMnO4. So this is actually oxidative cleavage or oxidative rupture of the carbon-carbon double bond of alkenes. As you rupture the carbon-carbon double bond, in order to get carboxylic acid, we are looking at RCH double bond like that. Then they will give you carboxylic acid, because otherwise, if it is a RCR like that, carbon double bond, they will give you ketones. And the other possibility is when you have HCH, meaning CH2 double bond, then you will get carbon dioxide and water. Anyway, so two different carboxylic acids. So let's have a look at these. The fact that they said two, that means anything which is cyclic. So if you look at option C, so when you have that thing there, and then that thing opens up, so when that thing opens up, your ring opens, but you will still get one product. So without thinking about whether it's carboxylic acid or not, it's still going to be one product. I can show you the product. It's just going to be, well, carboxylic acid there, and that will also give you carboxylic acid there. So 1, 2, 3, 4, 5, 6. This is a RCH double bond because there's one hydrogen there. This is a RCH double bond because there's one hydrogen there. So we follow that. So there are two carboxylic acids, but they are not in the different compound. They are one compound. So that's why C is automatically out. If I look at option A, So they've given a skeletal formula. So learn to read skeletal formula. Carbon form 4 bonds. So carbon here 1, 2, 3. So there's one hydrogen there. So what I can say is this one is a RCH double bond. So yes, that will give me a carboxylic acid. Whereas this next one is a carbon and a carbon there. So this is a RCR dash double bond. That will give me a ketone and not a carboxylic acid. So this is a RCR double bond. This will give a ketone, not carboxylic acid. So straight away, I know that A will be wrong because I want to get 2 carboxylic acid. As a matter of interest, well, if you have time, which you don't in an exam, I'm more interested in getting you to think about the concept. So this is a carboxylic acid product, and then this is the ketone product. So if I just highlight that with a black color, so that carbon there goes to that carbon, that other carbon there goes to this other carbon. So these 2 carbon were connected to begin with. Everything else is just the side chain there. Okay. B, if I have B, so B is actually the correct answer because I can see that when you rupture that bit there, so that carbon there and that carbon there, they are different. So the one in green, this is a RCH double bond. Carbon form 4 bond 1, 2, 3. There's one hydrogen there on the alkene carbon. This is the RCH double bond. This is also a RCH double bond because carbon form 4 bond, 4 covalent bond 1, 2, 3. So there's one hydrogen there as well. So what you can do is you can draw out the product, which I'm going to do now. So there is the first product for this thing on the left hand side. 1 carbon, 2 carbon, give you 2 carbon carboxylic acid called ethanoic acid. And then the next one is this carboxylic acid. So this is 1, 2, 3. This is called 2-methyl propanoic acid. Anyway, they're not expecting you to name them. So this is very clearly 2 different carboxylic acid. If you look at option D is not correct because it's a symmetrical alkene. I'll show you what it means by symmetrical. Well, probably you can see it already. This side is exactly the same as that side. That means, yes, you have a RCH double bond. Yes, you have a RCH double bond, but you will get the same products because the thing on the left is the same as the thing on the right hand side. So the only carboxylic acid product you get is going to be this thing here. And of course you can try and say, but they look different. Well, you know, they look different, but if you number them, so number 1 for the important carboxylic acid, 2 and 3, number 1 for the important carboxylic acid, 2 and 3, you got the methyl group at position 2. So both of these are exactly the same product, and they are just 2-methyl propanoic acid. So again, D is not 2 different carboxylic acid, there's just 1 carboxylic acid product there. Question 22, so this is about isomerism. They say the keyword is both. Cis-trans refer to geometric, so they can use this other term as they have used in the syllabus, and also optical isomerism. So here for cis and trans, there are 2 requirements. You must have carbon-carbon double bond because they will restrict rotation about carbon-carbon single bond, and you must have, what am I talking about? And 2 different groups on the same carbon of 2 different groups on the same carbon of carbon-carbon double bond. Okay, basically you cannot have 2 of the same group on the same carbon of the carbon-carbon double bond. As for optical isomerism, you must have optically active center. That actually mean a chiral carbon. A chiral carbon in this context refer to carbon with 4 different atoms or 4 different groups, 4 different atoms or group attached on that carbon that make it optically active. So having a look at the option, I should probably draw the options, I guess. I'm gonna draw slightly differently because I don't want to breach copyright or whatever other issues that might come across in the future. So this is one of the options given. So I'm just practicing my skeletal formula because I'm very good at drawing skeletal formula. So that's exactly what I'm doing here. So there's I there and there's Br there, and I will have that on the same side, chlorine and Br. That looks exactly the same. That is exactly the same as that, except this is Br and I, this is Br and Br. So I hope you can see immediately what I have said about the requirement for cis and trans as well as geometric isomerism. But in fact, cis and trans is geometric isomerism. You must have two different groups on the same carbon of the carbon-carbon double bond. Here you have Br and Br, so it doesn't matter if this is up or down, they are going to be impossible to have cis and trans because of these two things. So here, no cis trans. Although you have an optically active center there, that is your asterisk optically active center, 1, 2, and then hydrogen, and then all the rest of it. So onto the option B, we can obviously see the same chiral center here. And then now on your carbon-carbon double bond, you no longer have the same groups, or you no longer have the same atoms on the same carbon-carbon double bond. So I'm pretty sure that B is the answer that we're looking for. If I go for C, C has no optically active center because you can obviously see. Let me just draw it this way. It looks a bit easier this way. I am drawing skeletal, but it is exactly the same thing as what it will have looked like when it's displayed in front of you. So here I have Br, and I have CCl, and I have I there. So I have a chiral center option D there, but for the same reason as option A, I have two atoms. They are the same on the same side carbon-carbon double bond. No cis and trans, meaning no geometric isomerism. D cannot be true. Here I have two of the same atoms, Br and Br, so that means there's no chiral center. And the rest of the carbon, they are all carbon sp2, meaning to say this is carbon sp2, carbon sp2, carbon sp2. Carbon sp2 can never be chiral because you already have double bond on the carbon, and therefore you cannot have carbon bonded to 4 different groups if you already have double bond somewhere. So the answer there must be B. Question 23, so this is basically about reading the molecular formula. So if I just draw that correctly, reading the molecular formula from the skeletal formula. So carbon form 4 bond, that is very, very important. So molecular formula, what is the actual number of atoms for the different elements in one single molecule? So let's count the carbon first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there are 10 carbon, which means, well, all of them are 10 carbon actually in the options. So I have to count the hydrogen. Carbon from 4 bond. So carbon here is shown bonded to 1 carbon. So there's 3 hydrogen there. Carbon from 4 bond, 1, 2, 3, 4. So there's 0 hydrogen there. Carbon from 4 bond, 1, 2, 3. So there's 1 hydrogen. Carbon form 4 bond 1 and 2, so there are 2 hydrogen. Carbon form 4 bond again and again, 1, 2, 3, so there's 1 hydrogen there. Carbon form 4 bond, 0 hydrogen there. And carbon form 4 bond, there's 3 hydrogen there. And carbon form 4 bond, there's 1 and 2, so there's 2 hydrogen there. Carbon form 4 bond, so 1 and 2, there's 2 hydrogen. Carbon form 4 bond, 1 and 2, so there's 2 hydrogen there. So altogether, I hope you can see, if I make a mark on this one, 3 plus 1 is 4, plus 2 is 6, plus 1 is 7, 8 and 9, 9 plus 3 is 12, 12 plus 2 is 14, 14 plus 2 is 16. So there's C10, H16. We are looking at option C as our only answer there. Question 24 is about an ester, because I can see the RCO2R-. This thing refers to an ester. Well, not the CO2 molecule, but the CO2 within a compound. It basically indicates this particular functional group. This thing is your ester functional group. So what I have there is C15, H31, and then C double bond O, and then C16, H33. So this thing here is your ester, and what they have asked us to do is to hydrolyze in the presence of sodium hydroxide. Sodium hydroxide is a base, so this is called base hydrolysis or basic hydrolysis of an ester. So this is the bond I form when I form the ester, and this is the bond that I break when I hydrolyze the ester. I would expect to get C15H31, COOH, but this is acidic, and the acid will not survive in the presence of NaOH as a base. That is why I will not get OH acid. I will get O minus and then Na plus as a result of OH minus reacting with the acid to give you water, because there's neutralization to give you the salt when the acid, the carboxylic acid, reacts with the sodium hydroxide. On the other hand, the alcohol is not acidic. The alcohol is not acidic nor basic, so it just remains as an alcohol, which is not protonated or deprotonated. So we are looking at something that has Na plus, not both of them which are Na plus. So you can cross out A because both of them has got Na in the compound. So not both of them will get deprotonated, only the acid, because this is acidic and alcohol is not acidic. So A and B in fact are out for that reason. And then looking at C and D, your alcohol is the one that remains alcohol. And which one are we looking at? We are looking at C16H33, which is with the one with the OH. So be very careful what you're reading. So this is option D there, because option D will contain the C15H31 CO2Na and then C16H33 OH. So that's option D. Question 25. Let me have a read through this question actually. What in the world is this? Okay, so this is about oxidation of alcohol, but we are trying, it's very rare that we talk about electron movement in the context of organic chemistry, but then dichromate 6, which is obviously an oxidizing agent, is an inorganic oxidizing agent, but we also use it in organic chemistry, so it goes from orange to green color. So this is dichromate 6, and this is chromium 3 aqueous. So this is chromium plus 3, this is chromium plus 6, this is orange. Well, I mean to say the compound itself, the ion itself has orange color in solution, and there is green. So there's our usual coloration when it oxidizes an alcohol or an aldehyde. In this case, what do we have? We have 1 mole of Cr2O7 2 minus oxidizes 3 mole of X. So very important information there, and we are asked on what could X be. So based on the question given, we are told also that H2O going to that, and so that is basically whatever that one is. So this is the oxidizing agent. Oxidizing agent means we are looking at this being oxidizing agent, which means the organic compound, which means X as the organic molecule is the reducing agent. Okay, so if there's a reducing agent reduces the oxidizing agent, and the reducing agent itself is oxidized. Okay, the reducing agent itself is oxidized, and we are just given these two information for what happened in terms of a species that undergo oxidize. Well, this is the oxidizing agent, this is the reducing agent. Reducing agent itself is oxidized because it oxidizes the other substance. So this is oxidation, and the topic is actually oxidation as well. Okay, so let's have a look on what is going on here. Okay, I think I get the hang of it now. So this is just an extra information given. This is just for us to try and understand what is going on. So we just said that X being the organic compound reduces the Cr2O7 2 minus, therefore itself is oxidized. So both of these show oxidation. So I could imagine in option A is propanol, so CH3, CH2, CHO. So basically it's a 3 carbon aldehyde, propanol. What happened then is I will add H2O and I will lose electrons because I would form carboxylic acid, I will form propanoic acid. So it's not very clear from skeletal formula, so what I'll have to do is I'll have to use the structural formula, which is a bit clearer. and I'll have H plus, and I'll have electrons. Because I'm losing electron as I am getting oxidized, this is a half equation for oxidation, this is a half equation for reduction. Okay, and we know that 1 mole of these will react with 3 mole of these. So later we have to multiply by 3 after we balance the equation in order to get 6 electrons, because 1 mole of these requires 6 electrons. So for this to be true, our half equation must have 3 and 3, and therefore 6 electrons there. But first of all, we must try and balance it with just 1 mole of it first. Okay, so having had a look at it, I hope you can see that up until that point, they are the same. So I will have HO, but I have O2H. So I've added 1 oxygen to 1 oxygen. I've got 2 oxygen. So this is nice and happy. But now I have 1 hydrogen plus 2 hydrogen is 3 hydrogen. I only have 1 hydrogen there. 3 hydrogen giving me 1 hydrogen. So I need 2 more hydrogen there. So I have 2H plus. So all my atoms are balanced now, but my charges, no charge on the left, no charge. There is a charge there, 2 times plus 1 is plus 1, so I need 2 electrons. Now of course, based on the information given, 1 mole of dichromate requires 3 mole of X. So this is 1 mole of X. So if I put 3 mole of these, then I have 3 mole of these. Actually, if I just copy this, times 3, times 3, times 3, times 3 give me 6, times 3 give me 6 electrons. So does that make sense at all? Yeah, I think there's an answer already, because this is 3 mole of X will react with 6 electrons, and 6 electrons from the oxidation will be equal to the 6 electron from the reduction, because changes in oxidation number must be balanced according to your syllabus statement in the AS redox topic, because 1 mole of these oxidizes 3 mole of X. So 3 of these will give you 6 electrons that will balance out the 6 electron here. I think we already got our answer with option A there. I'll just very quickly show you for option B why it is incorrect, just to prove my point. If I have CH3, CH2, CH2OH, this is propan 1-ol in the option B there. So plus H2O, then I'll get the same thing, CH3, CH2, CO2H, propanoic acid. So up until here, they are the same again. But of course, then I'll also have H plus and electrons like that. So what is going to be different is I add 1 more oxygen, so I get 2 oxygen. I have 2 plus 1, which is 3 hydrogen, plus 4 and 5. So altogether I have 5 hydrogen here. I only have 1 hydrogen there, so I need 4 more hydrogen. And here is a H plus, so 4 times plus 1 means I have 4 electrons as well. Don't forget the information given. 1 mole of the dichromate requires 3 mole of X. This is 1 mole of X. When I multiply by 3, I multiply the whole thing by 3. I multiply by 3, I get 12 H plus. I multiply 4 electrons by 3, I get 12 electrons. 12 electrons do not cancel out 6 electrons based on this ratio, and therefore B cannot be the answer. You can try and do the same exercise for C and D, and you will find that they will not match up as well, because I already gotten the answer from option A there. Question 26 is about infrared spectrum. So with regards to infrared spectrum, we can see that no strong broad absorption. So the strong broad absorption at around 3000 to 3500 wave number, that is your typical OH bond. And then there is a strong, so there is a strong, sharp, well, reasonably sharp absorption. And this is at around 1750, wave number. There is indication of C double bond O. So no OH but has C double bond O. We can see that no OH would mean option C is out, option D is out, because no OH, no broad absorption around there, which could form hydrogen bond. And we have C double bond O, which is okay for A, which is okay for B. So how in the world are we going to differentiate between option A and option B? Let's have a look. Option A is this particular ester. option B is this cyclic ester. Let me have a read through the information. Okay, I've read the information. I actually should have, read the question from the very beginning. I would have done that if I have the question paper in front of me, but I am working from a screen. So I'm reading from the screen because, well, copyright issues. I can't produce the paper in front of you. But anyway, you will have the paper in front of you. Otherwise, you wouldn't be watching this tutorial because it makes no sense at all. The empirical formula for X is C2H4O. So all our job really is to go through the molecular formula by reading skeletal formula. So if I read through the skeletal formula, so 1, 2, 3, 4, there are 4 carbon, so C4. Hydrogen, carbon from 4 bond, there's 3 hydrogen there, 1, 2, and 3, because there's one bonded carbon here. Carbon from 4 bond, 1, 2, 3, 4, so no hydrogen. Carbon from 4 bond, they only show you 2, so there's CH2 there. Carbon from 4 bond, they only show you 1, so there's 3 hydrogen there. So 3 hydrogen, 2 hydrogen, 0 hydrogen, and 3 hydrogen. So 3, 6, 8. And I've got O2. That is molecular formula. You are expected to define molecular formula as well as empirical formula. Even back in year 9, where I'm currently teaching, empirical formula is defined as the simplest ratio of atoms in the compound. It's actually simplest ratio of atoms, not necessarily a compound, I beg your pardon. It's the simplest ratio, simplest whole number ratio of atoms. Okay, so I divide by 2 throughout, I get C2H4O. I've gotten my answer. There's no need for me to check for B. But you know me, in these kind of tutorials, I'm less focused on the exam thing, but more focused on the actual thing that you can do in exam. So there are 4 carbon there. And then there's 2 hydrogen, 2 hydrogen, and 2 hydrogen, and 0 hydrogen. So there's C4H6O2. You divide by 2, you're going to get C2H3O as your empirical formula, which is not what is given. So which means B is not the answer, and A is the only correct answer there. Question 27. So I hope I have enough space to do it here. I think I should do. Sodium metal. So we have ROH plus sodium. That will give you RO minus and a plus. So there is alcohol. So that is called alkoxide, sodium alkoxide. Then you will get hydrogen gas. But this is only one hydrogen atom. You want one hydrogen atom from the hydrogen gas. So you have half mole of the hydrogen gas. On the other hand, you have RCO2H. This is your carboxylic acid. It also has hydroxyl group, and they will give you RC double bond O minus, and a plus. Earlier, there was a question on base hydrolysis of ester. This is called carboxylate. Is what you get when carboxylic acid reacts with sodium metal. Here, they're asking us how many moles of hydrogen gas. You got to be able to appreciate that. 1 times hydroxyl, 1 times hydroxyl OH, whether you are in alcohol or carboxylic acid, gives only 0.5 mole of H2. So let's have a look at this molecule. HO and then CH2CO2H, CO2H, and then CH2CO2H. Let's have a look at how many hydroxyl we have. We have an OH there, another OH, another OH, and another OH. So altogether, you're going to get CO2 minus and a plus like that. Obviously, they are not expecting you to write down the product, but you never know what they might ask you in the future. So, it's not that difficult to write down the product. Don't forget that this is not a base. If it is not a base, it can react with alcohol as well, because that can react with metal to give you the hydrogen gas. So altogether, you get 0.5 multiplied by 4, which is 2 H2 gas, 2 mole of H2 gas from 1 mole of citric acid. So that's going to be option C as your only correct answer there. Question 28, this is about nucleophilic addition. I think nucleophilic addition, because this is about a carbonyl compound, which could be your aldehyde or it could be your ketone. Doesn't matter. Let me just show you an example of this mechanism using this aldehyde here. the first thing you would do is label dipole, delta plus and delta minus. You can find out more about this mechanism in detail in my A-level concept tutorial playlist. I never deleted those tutorial videos. They are all the A-level mechanisms that you're supposed to master. So there's one on nucleophilic addition in there as well. So the first thing that will attack the carbonyl is not your HCN molecule. Your HCN is a molecule, so it is slightly polarized, but it's not strong enough as a nucleophile. Instead, this first Cn minus come from the catalyst. So your catalyst is NaCN or KCN, which is going to be giant ionic structure, Na plus Cn minus or K plus Cn minus. So what it does is it attacks the electron deficient, electron poor carbon, and it breaks that bond. So what happened then is you will get this oxyanion intermediate. So this is a lone pair on that oxygen there. And then you have your HCN molecule, as I said, polarized. And from the lone pair of this oxyanion attacks the delta plus hydrogen and therefore kicking out the Cn minus, regenerating enough Cn minus to do more reactions with your carbonyl, your starting material. Ultimately, you will get this product which is called a cyanohydrine. So you have got an OH as well as a C triple bond N bonded to the same carbon, and you will also kick out Cn minus, and this is regenerated because NaCN or KCN is your catalyst. Don't forget, this reaction will also have to be done at cold temperature, like 15 to 20 degrees Celsius, because HCN boils easily. If your HCN boil off, then no reactant, then no products. Looking through the option, you can see that option A is completely bollocks because we are just talking about the catalyst being NaCN or KCN. So option A is definitely wrong. Option B, they talk about pentane 2-on. So pentane 2-on, really shouldn't be circling that actually. Pentane 2-on is 5 carbon, and that is pentane 3-on already. I should draw pentane 2-on, so 1, 2, 3, 4, 5. When I just get HCN added to it, what happened is this delta minus, delta plus. I know I will get a cyanohydrine, so I get OH and I'll get a C triple bond N. I should really maintain the habit of, drawing a correct skeletal formula. So this is a chiral product, and this is actually correct because a carbon there bonded to Cn, bonded to OH, bonded to one carbon, bonded to more than one carbon. This is a chiral carbon bonded to 4 different groups of atoms. Anyway, so B must be correct there, having crossed out C just now. How about options? Having crossed out A earlier just now, sorry. So this reaction is a nucleophilic addition, as I said earlier. In fact, we already said it earlier. Nucleophilic addition. Since we already said it earlier, then I can say option C is incorrect. Option D is also incorrect. Condensation means 2 things come together and will kick out a small molecule. Here you will see the 2 things come together and they don't kick out anything at all. This is definitely an addition reaction, not a condensation reaction, and it's definitely not a substitution reaction because you're not replacing one thing with the other. Question 29. So we have 4 reactions of propene. So this is about standard chemistry of alkene. I'm just going to draw, actually there's 4 carbon already. I'm just going to draw a skeletal formula. So this is prop 1 in. In fact, there's only 1 alkene for propene. Whether I draw the alkene here or here, it's still going to be prop 1 in or just propene. The first reaction in option A, there's just aqueous bromine. What you will get is bromination, but of course you can get other mixtures because you are using not liquid bromine, you are using aqueous bromine, so you can get Br and OH, a mixture of the products where the OH from the water can actually compete with the Br minus to give you your final electrophilic addition product. Now you have a cold dilute acidified KMnO form. This is also oxidation. In one of the earlier questions, I forgot which one, there was a question of using hot concentrated KMnO4 that will cleave, that will rupture the carbon-carbon double bond totally. But this is a mild oxidation. These are conditions for mild oxidation of carbon-carbon double bond. You will just get diol. And this is oxidation because above the carbon of the carbon double bond, gain oxygen. And you have learned this back in O-level IGCSE chemistry, gain of oxygens, oxidation. Okay, what about C? C is going to give you HCl, so this is option C. You're adding hydrogen chloride, so there's no competition with water whatsoever. You can get the chloride added there, or sorry, I meant to say plus, because you could get major and minor product. As a matter of fact, this is going to be the major, this is going to be the minor. How do I decide that? Well, you can think about cutting out the chloride, then you can get this carbocation, and you can think about cutting that chloride out, and you can get this carbocation. Then the Cl minus attack the carbocation. Looking at the carbocation, the carbon with the positive charge is bonded to one other carbon. This is what you call a primary carbocation. Is only stabilized by one inductive electron with donating group. Okay, the carbon with the positive charge is bonded to two other carbon. This is what you call a secondary carbocation. So they are stabilized by two electron donating alkyl groups there. Okay, last but not least, we also have, should really use green just to be consistent, I guess. Style, make it into green. Okay. You have steam. So this reaction with steam doesn't work on its own. You also need concentrated H3PO4 catalyst, and of course around 200 to 300 degrees Celsius. What will happen is you would form alcohol, but you can also get the other product. Of course, major versus minor is going to be the same as that. I would say this is the major, this is going to be the minor product. Now there's option D there. Now, which row is correct? Let's have a look through the options and think about it. So first row, they say you just get 2-bromopropane. So 2-bromopropane would mean you get something like this. This will have been plus HBr. This will have been something like option C here, which of course this is not option C. You're not adding HBr, you're adding Br2. A cannot be the answer there. Okay, if you form this, then you need HBr. On the other hand, then you have propane 1,3-diol. This is position 1, 2, and 3. This is called propane 1,2-diol because the OH is at position 1 and position 2. So 1 and 3 is incorrect. It should be propane 1,2-diol. Left with the option C and D. Hydrogen chloride, they did say the main organic product. So the main organic product is the major product. This is going to be 1, 2, and 3. So this is 2-chloropropane, and this is correct. So there's your 2-chloropropane. So we got our answer C as our only answer. And why is D wrong? Because this is the minor product. This is propane 1-ol. So propane 1-ol is not the major product. Propane 2-ol is the major product. You can have a look in your structured paper. Very popular question explaining major versus minor in terms of the stability of the carbocation in this electrophilic addition mechanism. You can find out more from my A-level concept tutorial playlist under electrophilic addition if you are interested. Question 3, the last question in this section A. So what we have is butanoic acid from 1-bromopropane. So this is 1-bromopropane, 3 carbon, and I get butanoic acid. So butanoic acid is 4 carbon. So 1, 2, 3, 4. This is 4 carbon. I have added carbon. If I have added carbon, I should be thinking about cyanide. So things like C triple bond N. This is 1, 2, 3, 4. This is called butane nitrile. That's how you name nitriles. You see the CH, triple bond N, there's your nitrile, 4 carbon, starting from the important carbon, butane nitrile. So first of all, I do need a nucleophilic substitution, and I would need KCN. I would need like KCN or NaCN in ethanol, and I need to reflux this. And of course, then this is just hydrolysis. Hydrolysis has to be the acid hydrolysis of nitriles because I am not obtaining a salt, I'm obtaining carboxylic acid, so I have to do it in acid. So things like dilute HCl and reflux will do the job. So this is my intermediate compound that is required, partly because I've noticed that added carbon. Okay, so this has to be option D. Looking at section B type of questions, the logic is always to check option 2 first. So without further ado, let's jump straight onto question 31. I mean, you have been accustomed to what option A, B, C, D actually means to you, so I assume you know what I'm talking about. So this is the equilibrium shown. This is the alcohol plus CH3CO2H. This looks like a long question, but we never know until we actually check the options. So it could be nice and easy. No one knows, all right? So delta H is minus 6 kJ per mole there. We are given the MR, so there is 46 for the alcohol, 60 for the acid, 88 for that ester, and obviously 18.0 for the H2O, which you can get from the data booklet. If I talk about the initial mole, initially I have 9.2 gram of that. I have 12 gram of ethanoic acid, so 12 over 60. I have 8.8 gram of that. Press the enter your calculator. I get 0.2, 12 divided by 60, I also get 0.2 mole. 8.8 divided by 88, I get 0.1 mole. And then at equilibrium, so mole at equilibrium, I found out that I only have I now have 4.8 gram of ethanoic acid. Sorry, there is no ethanoic acid, I beg your pardon. 4.8 mole of ethanoic acid means that this equilibrium has shifted backward because I started with 0.2 gram of this, I end up with 4.8 gram of that, of ethanoic acid. This is gram, this is mole, so 4.8 divided by 60 is going to be the mole of the ethanoic acid at equilibrium. I have obtained 0.08, or actually the mass has decreased, so the mole has decreased. I beg your pardon, this equilibrium is actually going to the right hand side at equilibrium. Anyway, so from 0.2 to 0.08, how much has reacted? So 0.2 minus 0.08, so 0.12 mole of acid reacted. Looking at the balance equation, 1 mole of these react with 1 mole of these to give you 1 mole of these and 1 mole of water. So what do we have? If I think about it, if I have the mole of, if I produce, let's see, how can I, okay, the mole of ester form over the mole of acid reacted is 1:1. So as a result of that, I hope you can see, I don't know why this is not doing its job properly. So as a result of that, if I want to know how much ester is formed based on how much, of the carboxylic acid reacted, which is 0.12. So, the mole of ester formed is going to be 0.12 mole. You started with 0.1 mole of the ester, and now you have plus 0.12 mole. So yeah, I mean, I could get 0.1 plus 0.12. I'll get 0.22 mole. Now, if this much mole of acid reacted, this much mole of alcohol will react as well, because 1 mole react with 1 mole of that. So if 0.12 mole of this react, 0.12 mole of the alcohol react as well. So minus 0.12 mole. And I get 0.08 mole. Now onto the water. Remember that if you produce 1 mole of ester, you also produce 1 mole of water. So you started with no water at all, and now because you produce 0.12 mole of ester, you produce this much ester. So if you produce 1 mole of this, you produce 1 mole of water. If you produce 0.12 mole of ester, you also produce 0.12 mole of water. So these are all different numbers altogether. These are quite complicated actually. So if I look at option 2, I should really have checked option 2 first. I don't know. I mean, I could be wasting my time here. Okay, let's see. The equilibrium mixture at 323 Kelvin will contain more than 4.8 gram of ethanoic acid. So this thing, statement number 2, okay, if we look at this this info was at 298 Kelvin. Forward reaction is exothermic because it's negative 6 kJ per mole. That means our forward reaction release heat. As temperature increases at 323 Kelvin, so what happens when temperature increase? The system or the equilibrium will try to decrease temperature. It will try to oppose the change. It will try to decrease temperature. We only know how to release heat. Exothermic means release heat. So if we want to decrease temperature, therefore system will release less heat. If system release less heat, therefore favor backward reaction or shift to the left. When you shift to the left, we are looking at ethanoic acid, which is on the left hand side. Ethanoic acid is on the left hand side. So you started out with 4.8. What are we talking about? Equilibrium mixture is at 4.8 gram. So when you increase temperature, equilibrium shift backward. So equilibrium shift backward and favor backward reaction. You will get more of these. You will get more of 4.8 grams. So therefore more than 4.8 gram of CH3CO2H. So that means option 2 is actually correct. Okay. What about option 1? There are 0.22 mole of the ester at 298 Kelvin. So this was done at 298 Kelvin. This was the mole of the ester. So 0.22 mole of the ester at equilibrium. So this is statement 1, which is also correct. Now, how about statement 3? Statement 3 is saying that if I add a small amount of water at the start of both experiment or either experiment, the value of Kc will not be affected. And option 3 is entirely correct because in either experiments, so both experiment, what are we talking about? Both experiment. Yeah, okay. So both experiments will be at the same temperature. So we are saying that the value of Kc will not be affected. So adding water, adding H2O means changing concentration. We are just changing the concentration of H2O, not the temperature. Therefore, Kc remains constant, and the Kc for the different temperature will be different obviously, but then the Kc at each respective temperature will remain the same because temperature is not changing, only concentration is changing, which means equilibrium will change position, yield can change, but your Kc will remain constant. So 1, 2, and 3 are correct. We are looking at option A, where 1, 2, and 3 are actually entirely correct there. Question 32, this looks like energy profile diagram. So if you think about this energy profile diagram, the reactants have lower energy than the products. So if we think about enthalpy change, it's always from the reactant to the product. So we are heading upward. So we're looking at endothermic. So there's the information you can get. Endothermic reaction profile diagram. Usually I would say look at option 2 first, but I can obviously see option 1 being thermal decomposition. Thermal decomposition is a O-level or IGCSE level chemistry, which of course you revisited in AS chemistry under group 2. From the solid to the solid and the gas, you need heat. If you need heat for this reaction, it's definitely endo. Now I will check option 2, H2 gas going to 2 hydrogen gas. This is actually this enthalpy change. This delta H is equal to 2 times the atomization of hydrogen, because you are forming 2 mole of the gaseous atom from its elements in its standard states under standard conditions. That's why we have 2 times the atomization, because atomization is defined for forming 1 mole of the gaseous atom from its element in its standard states under standard condition. This thing is also equal to the bond energy of the hydrogen there, because we are breaking, is the enthalpy change for breaking 1 mole of the covalent bond into gaseous atoms, everything in the gaseous state. So both of these are actually equal, but both of these would definitely be endothermic because you need energy to do these processes that I just talked about. Number 3 is about chlorine aqueous going to chlorine gas. plus aqueous. This is slightly unorthodox, meaning it's not common. What is more common is to think about something in your AS called enthalpy of hydration. Enthalpy of hydration is always exothermic, whether you are cation or anion. So what it means is from the gaseous cation or gaseous anion, meaning gaseous ion, dissolve in a large amount of water to give you hydrated ions. Okay, so you're very far apart and suddenly you're surrounding yourself with water. So you have these chloride ions. They will form partial bonds with this polar water molecule. These are not complex or anything. They are just being surrounded by a lot of water. Of course, you have the delta plus on the hydrogen that can form this thing called ion dipole. Dipole from the H2 or water molecule, which are polar. Ion from the fully charged cation or the anion. Ion dipole bond formation means that this enthalpy of hydration is always exothermic. We are going the opposite way to enthalpy of hydration. Going from right to left is enthalpy of hydration is always exothermic. Therefore, this thing is endothermic because you're going opposite way to the enthalpy of hydration. So number 3 is also endothermic. 1, 2, and 3 are entirely correct. We are looking at option A for question 32. So in this next question 33, looks a bit tricky, but what do we know about density? So density is mass over volume, as you can tell from the unit, gram over dm cube. What do I know about density? What is important also is gaseous. So what do we know about gases? We know about gases as the molar volume of gas, which is 24 dm cube per mole of any gas at room temperature and pressure. I think that is part of the hint given under room conditions. So what do I know? 2.42 gram per dm cube. If I think about if I have, or actually I do have the answer, because 2.42 divided by 1 dm cube, gram per 1 dm cube, gram per dm cube means per 1 dm cube. That means in 1 dm cube there is 2.42 gram. So in 1 dm cube of gas, there's 2.42 gram of the gas. This is volume of the gas, so the mole of the gas, which is 1 dm cube divided by 24 dm cube per mole, is going to be mass over mr. So 2.42 gram divided by mr of the gas. So I think this is the information you can get from it. The volume of the gas in 1 dm cube divided by 24 is going to give me the mole of the gas, which is going to be the same as the mole of the gas based on the mass over the mr. So my job really is find the mr of the gas. So this brings up and this brings up. 24 times 2.42. I get 58.08. So this is mr, so it's gram per mole. Now I'll have a look at the options. So option 2 first. Let me check that. Oh, that looks ugly. So I have 1, 2, 3, 4. I have 4 carbon, C4H. And then I have 1 hydrogen there because carbon form 4 bond. So 1, 2, 3, there's 1 hydrogen. There's 3 hydrogen because carbon form 4 bond. There's 1 short, 1, 2, and 3 hydrogen remaining. There's 2 hydrogen there and 2 hydrogen there. This is really an exercise of reading skeletal formula. 3, 4, 5, 6, 7, and 8. C4H8. So the mr is going to be 12.0 times 4 plus 8 times 1.0. I get 56, not 58. So number 2 is definitely wrong. Therefore, only option 1 is correct without even checking for number 3. Because number 3 will also be C4H8 as it is but2int is an alkene with 4 carbon. C4H8 will give you 56 again and not 58. If number 2 is wrong, number 3 is automatically wrong as well. Let's check for number 1. So this is C4H10, this is butane. And I can automatically see there's 2 extra hydrogen. So 56 plus 2 will give me 58. So mr of C4H10, you can check 4 times 2 is 48 plus 10 is going to be 58, which is going to be that. I have calculated based on the density given. 2.42 gram in 1 dm cube allows me to do that particular calculation like that. Only one is correct. We're looking at option D there. Question 34 is about shape of molecule. So they want contain at least one. They just say at least one. They don't say just 120-degree bond angle. So if we look at number 2, option 2, there's PF5. So there's phosphorus with 5 bond pair because fluorine forms single covalent bond. So this is 5 bond pair, 0 lone pair. The 5 bond pair repel equally, and this will give you a trigonal bipyramidal geometry. So it's a bipyramidal because you have a pyramid on top, a trigonal pyramid on top, another trigonal pyramid from the bottom. So the base is essentially trigonal planar, so that's 120-degree, but then that is 90-degree. So you do have your 120-degree, at least one of the angle is 120-degree. On to option 1, you have C2H4. This is ethene molecule. So this is C2H4, like that. We count the sigma bond. So there is 1, 2, and 3 sigma bonds around this carbon. So around that carbon, 3 sigma bond. I should probably write sigma a bit better. Would mean 3 bond pair of electrons and 0 lone pair because you use all the 4 electrons for bonding, 1, 2, 3, and 4. So what happened is the 3 bond pair repel equally. When the 3 bond pair repel equally, what you're gonna get is trigonal planar and 120-degree. That means we also satisfy again one of the angles is 120-degree. Next but not least, well, last but not least, I don't know what's wrong with my language today. Anyway, so you get this trigonal pyramidal, which I have shown using this geometry. This is flat, this is pointing towards you, coming up from the screen. This is away from the screen. Because there's 3 bond pair, you count the sigma bond. You have 5 outer shell electrons, 3 of which are used for sharing. You still have 2 more. So you got 1 lone pair. The bond pair, lone pair repel more than bond pair, bond pair. This is just like ammonia. So this is going to give you trigonal pyramidal, and trigonal pyramidal is going to be 107-degree, none of which are going to be 120-degree. So there's no 120-degree at all. This is option 3. So only 1 and 2 are correct. So only 1 and 2 are correct, not 3. So therefore this is option B there. Question 35. Oh, very wordy. This is period 3 chemistry. So it's going from sodium all the way to chlorine. If I check number 2 first, the radius of the most common ion. What is meant by most common ion? Well, you have the cations from the group 1 to 3. I should really use the Arabic numeral 1, 2, and 13. And then you have the anions from the 14, 15, 16, and 17. Typically, we don't include the 14, the silicon. We just look at 15, 16, and 17. If I just sketch out what we know about going across a period, across period 3, we have atomic radius decreasing across the period like that. We also know that the cation is smaller than the parent atom, and the anion is bigger than the parent atom. So this would be like P3 minus and then Cl minus there. That would be like Na plus and Al3 plus like that. Looking at the statement, the radius of the common ion decreases. The radius of the common ion decreases, but it doesn't decrease all the way. Okay, so the radius there decrease, but then it increased there. If you look carefully, there is where it increased. So there's a cutoff point because we don't know where silicon really lies, whether it like to lose or gain electrons. But essentially, yes, it decreases from sodium plus to Al3 plus, but then it increases. It increases from the metal to the non-metal. So that is the real important deal here. Your statement 2 talk about decreases, and that is wrong because it does increase. It does increase from radius of L3 plus to radius of P3 minus. If you don't believe me, you can have a look at the data booklet. Your data booklet show you ionic radius for free, which of course you can have a look. From there to there, there's an increase in the ionic radius. So this thing is for real. This is reality, which means we are not accepting option 2 there. If option 2 is wrong, then only option 1 is correct there. Okay, and of course option 3 is wrong as well by default as a result of these. And you can also imagine that across a period, when you go across a period, your shielding is roughly constant. So we don't talk about the shielding decreasing across a period because you're filling in the same shell just as if you're sitting in the same row in the cinema. So only one is correct. We're looking at option D there. Question 36 is looking at correct statement for group 2 chemistry. So group 2 chemistry is in S, straight after general periodicity. If we look at option 2, we are looking at solubility of the hydroxide. In AS, they expect you to be able to state the solubility of the hydroxide, which actually increases down group 2 as the radius of the cation gets bigger. And this is an essay, 4 to 5 mark essay in an A2 setting, in an A2 paper 4 actually. So that is barium hydroxide, and let's say there is magnesium hydroxide. Magnesium hydroxide is not very soluble, which is why the pH of magnesium hydroxide, when you dissolve MgO in water, it's only around pH 9, but barium hydroxide is pH 14, very soluble in water. So calcium hydroxide, calcium comes somewhere, well, not that high up, but calcium comes somewhere there. Calcium hydroxide is more soluble than magnesium hydroxide, so number 2 is definitely correct. Number 1, this is about temperature for decomposition. So as we know about radius of the cations, as the radius of cation gets bigger, actually I don't need to draw a graph actually, as the radius of cation gets bigger and bigger, the M2 plus become less polarizing. It means it distorts the electron cloud on the CO3 2 minus lesser, because charge density, I can't even write properly now, charge density of the M2 plus, which is equal to charge over size or charge over volume, would decrease because you have the same charge going down group 2, but the size is increasing because more shells. Okay, so charge density decreasing would mean they become less polarizing, therefore CO bond is less weakened. So this is actually another 3 to 4 mark essay in A2, which of course in AS you're just expected to be able to state the trend. I'm just saying it's a lot easier to say the trend after I remember what is going on in each step. So therefore harder to break. Harder to break the CO means harder to decompose the carbonate. Harder to decompose the carbonate means temperature of decomposition is higher going down to group. So I do end up drawing this thing. So this is temperature of decomposition going down to group. Harder to decompose going down group to carbonate. So magnesium carbonate is somewhere there. Calcium carbonate is somewhere there. So we don't know it's a straight line, it's just a trend. It gets harder to decompose down group 2. Magnesium carbonate decomposes at a lower temperature than calcium carbonate. Number 1 is definitely correct. Number 3, this is talking about reducing agent. So magnesium, calcium, and then barium. Going down group 2, so down group 2, easier to lose electrons because you have valence electron, more shielded because more shells. You have more inner shells, more shielded. Easier to lose your electrons because your effective nuclear charge decreases down the group as a result of shielding winning over the increase in nuclear charge. So your valence electron becomes less attracted, easier to lose electron. When you become easier to lose electron, that's the key factor here. Therefore, easier to lose electrons, easier to be oxidized. If you become easier to be oxidized, therefore better reducing agent, because you really want to lose electron more, you become better reducing agent. So calcium is below magnesium. Calcium is a better reducing agent. Calcium is a stronger reducing agent than magnesium, so that's entirely correct. If you look back at your reactivity series from your IGCSE or O-level metals, Porso, Carmazil, calcium is above magnesium in the reactivity series because calcium prefers to lose electrons more than magnesium for this entire reason. 1, 2, and 3 are entirely correct, so we're looking at option A as the answer for question 36. Question 37, which statements are correct? So we're looking at correct statement there. If we look at option 2, we have 1,1-difluoroethane. So if I just draw ethane first, and then I would draw 1,1-difluoro, I can tell you they are definitely polar because you have a tetrahedral geometry, and then, well, tetrahedral there. And then not all the atoms are the same, not all the are fluorine, so that means the dipoles don't cancel out. Okay, if the dipoles don't cancel out because you don't have the same atoms, on the same carbon in a tetrahedral environment, so that is polar. So the 1,1-difluoroethane is polar, is actually correct. On to statement number 1, difluoroethane versus dichloroethane. So you have F like that, 1,1-difluoroethane versus chlorine like this. So we know the energy of a CF bond is stronger than the energy of a CCl bond because this is a shorter bond, shorter covalent bond. Therefore, it's a stronger covalent bond. This is stated in the topic of covalent bonding in your structure and bonding topic in AS. So it is less reactive because it has got a stronger bond. Therefore, anything with the CF is less reactive since you require a lot more energy to break. So that is actually correct, which is why these undergo free radical reactions but not the CF bond. Looking at, well, option 3, I already answered option 3 because option 3 is basically about the bond energy. The CF bond is stronger than CCl. You can get it from data booklet if you want to, but I have just obtained it by thinking about the size of the halogen and therefore the length of the covalent bond, and therefore relate the length of the covalent bond to the strength of the covalent bond. Question 38, you want to distinguish. Distinguish means to tell apart, to differentiate, and you want to use alkaline aqueous iodine. Alkaline aqueous iodine is the iodoform test. So iodoform test. Iodoform is this thing called triiodomethane. There are 3 iodines bonded to 1 carbon. Triiodomethane is the official name. Triiodomethane. So in your syllabus, these are broken down into 2 separate positive tests. It's either CH3CHOH or CH3C double bond O. This come under the carbonyl topic, this come under the alcohol topic, so we have to check through one by one. If we go through option 2, we have pentane 2 on. Nope, there's pentane 3 on. This is pentane 2 on. 1, 2, 3, 4, 5. And then we have pentane 3 all. This is alcohol, careful. This is pentane 3 all. This is pentane 2 on. So let's have a look at if we have CH3CHOH or CH3CO. We do have CH3CO, no positive test. Well, basically there is no CH3CHOH because it's CH3CH2OH, well, CH3CH2CHOH, which is not this. So you don't get positive result there. So this result tick and cross refer to with alkaline aqueous iodine. So I can tell the difference, can differentiate, can distinguish, because one is positive and the other one is negative. How about option 1? Option 1 is butanol. So there's 1, 2, 3. Oops, I'm missing 1 carbon. Versus butanol. So 1, 2, 3, 4. You can draw this thing here, but this will also be butane 2 on because you number the most important carbon, which is a ketone with the smallest number. I can hopefully make you see that there's a CH3CO there, just like CH3CO there, but there is no CH3CO or CH3CHOH. So this will be positive test, this will be negative test, therefore can distinguish, can differentiate. So that means option 1 is also correct. Okay, I should put a tick on it. Last but not least, if I check option 3, option 3 is propanol. Propanol has got the CH3CO, so obviously it's positive test. Propan 2-ol, so this is 1, 2, and 3. I have also got CH3CHOH. If I write the structural formula, then it will make more sense. This is your CH3CHOH, so this is also thick. which means that you cannot distinguish, cannot tell apart the difference, cannot tell apart differences. So only 1 and 2 are correct. So therefore, we're looking at option B being the correct answer there. Question 39. So getting to the end now. You want to have colored organic product. So not a lot of organic product will be colored. We are looking at the 2,4-D and pH with carbonyl compounds, and I guess, yeah, okay, I can tell you, okay, they are very tricky. Organic product that is colored, okay, organic product that's colored. I'll tell you why number 2 is not correct, because when you think about ethanol, you react it with acidified dichromate 6, Cr2O7 2-. This thing is chromium plus 6, which is orange dichromate 6, and this thing will go to chromium plus 3, which is green in color. So the color is due to transition metal and not organic compound, because people think about the color changes and they forgot that this question is asking you about the organic compound. So you will get ethanoic acid if you reflux it, or you can get ethanol if you heat and distill immediately. None are colored. These are organic compounds. None of them are colored. They are trying to confuse you to think about colored reaction mixture versus colored organic products. So be very careful of what they are trying to ask you. This question can be changed to colored reaction mixture, then 2 will be correct, but this one specifically is asking you on colored organic product. So 2 is incorrect. Number 1 is definitely the correct answer. In fact, that's the only one, which means option D is the correct answer. I'll very quickly show you what number 1 is. It's an aldehyde, so it's 1 and 2 is ethanol. So aldehyde can react with 2,4-D and pH, which stand for dinitrophenyl hydrazine. So you're not expected to know the formula of it, but it's quite useful to think about what is happening rather than just, memorizing things that don't make sense to you. Phenyl group is this C6H5 ring, but of course you don't have 5 hydrogen in the ring. You have substituted the hydrogen with NO2 and NO2 at position 2 and 4. These are nitro group, 2,4-dinitro. Phenyl. Hydrazine is this NH-NH2 group there. It's got the lone pair there. It's got the carbonyl there. This is a classic condensation reaction. Condensation reaction because you will kick out a small molecule, water in this case. The O get kicked out, the H and the H get kicked out. So what happened then is you get that nitrogen, and that is still the exact same thing. And you kick out the H2O because 2 hydrogen from there and 1 oxygen from there. This nitrogen has now added onto there. Condensation because you kick out a small molecule, not just addition. Addition would mean 2 things become 1 thing. Condensation, 2 things come together, kick out a small molecule. Alright, and this is very well known as an orange crystal, orange solid, orange precipitate. So it is this organic compound that is actually colored. Question 40, finally reaching the end of this paper. So what do we have? We have propanoic acid, so 3-carbon acid, 1, 2, and 3. We react it with excess lithium aluminium hydride. This is a reducing agent, so it's a reducing agent. It will reduce the aldehyde all the way to your primary alcohol, where the carbon with the OH is bonded to one other carbon. This is called primary alcohol. And then the organic product of this reaction is reacted with ethanoic acid, so 2-carbon carboxylic acid. This is propane 1-ol, 3-carbon alcohol. And you have 2-carbon acid, which is ethanoic acid. So what you're going to get in the end is you're going to get an ester. You're using corn sulfuric acid as your catalyst. So I will have my O. But I will kick out the H and I'll kick out that's not a very good color. I will kick out the H and I'll kick out the OH there as my condensation reaction. So like that, and then I'll kick out H2O. So this is the ester bond that you form. This is also the ester bond that you will break if you do hydrolyze it. And this product X is an ester. X is ester. What is the use of ester? Well, you can use it for solvent. Why is that not working? You can use it for solvent, so that is your option 2, that is correct. You cannot use it as a fuel, but you can use it as a flavoring. So number 3 is definitely correct. But number 1 as a fuel, you don't use it as a fuel. It's not a hydrocarbon. Doesn't burn as well as just hydrocarbon, which is compound containing carbon and oxygen only. So you don't use this one as a fuel. 1 is wrong. Only 2 and 3, which means you're looking at option C. Alright, we've reached the end of this tutorial. Don't forget to click the button on the bottom right to subscribe to the channel if you found my tutorial useful. Do browse around the channel for other useful tutorial videos. And please subscribe to the channel and share the channel widely with all your friends, chat group, juniors, seniors, teachers, relative, and yeah, whoever else you think might benefit from these tutorial videos. Follow me at ptet.chemistry. Across the backdrop, like the not the backdrop, what am I talking about? The watermark behind this video will have ptet.chemistry on Facebook, Instagram, and Twitter. So I look forward to getting connected with you there, where you can send in messages and questions and stuff. And yeah, I'll see you in the next tutorial video. Thank you for watching.